In this video, we're going to show that the distance from a point to a set is a Lipschitz function, and my goal is to keep this video self-contained, so I'm going to try to introduce all the relevant definitions along the way. So the first definition that we need to be comfortable with. What is a metric space so far? So usually we denote a metric space by pair x comma d, and what does it mean for that to be a metric space? So x is just a set, just any set, and d is a function from x cross x to the real numbers. So in other words, you input two things from x and it spits out a real number, and d has to satisfy four conditions. The first condition d has to satisfy: for any 2 points x, y in your space in your set x, the distance from x to y has to be non-negative. Number two, for any 2 points x and y in your set x, the distance from x to y is 0 if and only if x is equal to y. Number three, the distance from x to y is the same thing as the distance from y to x. And the last one, number four, for any 3 points x, y, z in your set, the distance from x to y is less than or equal to the distance from x to z plus the distance from y to z. That last one is called the triangle inequality, and it's going to show up later. We're going to use it later. Now let's let A be a subset of x, just any subset of my set x. Now for a particular point x in my set x, we're going to define the distance from that point x to the set A we're going to denote it by dx capital A. So we're still using that kind of distance function notation like above in the red. We're going to define it as the distance from x to the set A is going to be the infimum of all the distances from x to any point in A. So it's the infimum over all distances from x to any individual point of A. Remember, the infimum is the greatest lower bound. I've got a little picture for you over on the right to try to motivate what the heck I'm talking about. So I've got my set X, I've got a little purple subset A, and I've picked out a white point X that's in my set X. And what I'm saying is, I'm trying to draw some dotted lines that illustrate the distance from X to points in A. And I'm saying that the distance from X to the set A should be the smallest of all such distances, which in my picture I think is the yellow, just according to how I draw it, artist's interpretation. So that distance to the set should be the smallest of all the individual distances, all the distances to the individual points of A. All right, the next definition that we want to be comfortable with. Let's say you had two metric spaces, x and y, and just for convenience, let's say the metric on x is dx, so like the distance function on x is dx, and similarly the metric on y is d sub y. Now let's say I had a function that goes from x to y. So, x is the domain and y is the codomain. We're going to say that f is Lipschitz, or it's a Lipschitz function on the set x, if there exists a real number that's positive, call it k. So if there exists a positive real number such that for any 2 points in the set x, so for x and x prime and x, we have that the distance from f of x to f of x prime is less than or equal to that number k times the distance from x to x prime. And again, the caveat here is that that number k needs to work for any pair of points in my set. It's got to be the same k for any pair of points in order for this to be Lipschitz. Now there could be more than one k, right? But I'm saying that for a k that you pick, that k needs to work for all the points in the set. Now, we're going to rearrange this a little bit. So assuming x is not equal to x prime, then I know that over there in the orange, I know that's non-zero, so I can divide. So if I divide both sides by the orange, I see that I get this fraction on the left. And what I want to do is I want to interpret this kind of like a college algebra or a calculus 1 kind of setting. What does this say? If you think about the left-hand side is sort of like the average rate of change in my function between the points x and x prime. So another way to think about what it means for a function to be Lipschitz is to say that the average rate of change in my function f between any 2 points is at most k. Remember maybe the average rate of change, if you thought about that in college algebra, that was the slope of the secant line between those 2 points. And why is this, useful? And so this could be useful if maybe f is a function that we're trying to use to maybe classify some objects. Now, if x and x prime, my inputs, if they're similar objects, I want them to be classified as similar objects. And so if x and x prime are similar, you might take that to mean that the distance between x and x prime is small, however you measure distances. And then what we'd expect then, if f is Lipschitz, we'd expect that f of x and f of x prime are going to be similar objects as well, because the distance between the outputs is just this constant multiple of the distance between the inputs. So if the distance between the inputs is small, then I expect the distance between the outputs to be small too. And that would be good. That means f is a good classifier if it's small. In other words, there's not much distance between the outputs, and that's good. That's what we want. Okay, so let's get back to what is the point of this video. The point of this video is to prove the following proposition. So let's let xd be a metric space, and let's say a is a subset of x. Let's define the function f from x to the real numbers by f of little x is equal to the distance from x to a. So you plug in a point x from little x, and it spits out the distance from that point x to the set a. And what I claim is that this function f is a Lipschitz function. We're going to go through the proof of this now. So let's let x and x prime be two elements of the set x, and let's let a, little a, be an element of the set a. And what we're going to do is we're going to apply the triangle inequality in the following two scenarios. I'm going to go ahead and list out the two scenarios now, and then we'll go through them individually. Now, what I'm going to start with is, if I think about the distance from x to a, the triangle inequality tells me that that's less than or equal to the distance from x to x prime plus the distance from x prime to a. Scenario 2, what if I start with the distance from x prime to a? Again, triangle inequality tells me that that's less than or equal to the distance from x to x prime plus the distance from x to a. Now that we've got the scenarios laid out, let's jump back to 1 and just manipulate it, and you'll see where we're going to stop. So the first thing I'll do is subtract the distance from x to x prime to the left side. And notice that this inequality is true for all elements a of the set A. Now, I want to notice here, the thing on the left, what does that say? That says that's less than or equal to dx prime a for all a and a. That says that that in green is a lower bound for the set of all distances measured from x prime to points in a. But what do I know? I know that the distance from x prime to the set A is the greatest lower bound. So that means that's bigger than any other lower bound I've got my hands on. And so if I take that and put it into symbols, I'm trying to say that I know the green has to be less than or equal to the purple. So that's by definition, again, of a greatest lower bound. Now what we're going to do is manipulate this. Let's just add the distance from x to x prime back over to the right side. And now, what else do I know? If you've noticed, all I've done is I've swapped out the little a on the left for a capital A on the left. And the reason that I can do that is because, again, the distance from x to the set A is the smallest of all such distances from x to any point in A. Finally, we'll do a little bit more algebra. We'll just move the distance from x prime to a back over to the left side by subtracting, and we obtain, if I zoom in a little bit, the distance from x to a minus the distance from x prime to a is less than or equal to the distance from x to x prime. Now, we're not done yet, even though maybe it looks like we might be done. What we're going to do is we're going to go back up to scenario 2, and we're going to run through a similar argument. So, similar ideas, let's subtract the distance from x to x prime to the left side, and we'll notice that that is true for all elements little a in the set A. And again, what does that say? That says what's in blue is a lower bound of all distances from x to any point in A. And we remember that, well, the distance from x to the set A is the greatest of all those lower bounds. And so if we put that into symbols, we obtain that the blue is less than or equal to the purple. Now what we'll do is a little bit of algebra. We'll add the distance from x to x prime back to the right side. And what I claim is, again, on the left, I can swap out the little a for the capital A. And that follows again because the distance from x prime to the set A is the smallest of all distances from x prime to any individual point of A. Finally, we'll do some algebra where we will just subtract the distance from x to the set A back to the left side. And now we've got something similar at the bottom of both scenarios 1 and 2. And I want to compare what they look like, and what I hope that you notice is on the left side, they just differ by a sign, right? One is the negative of the other, and on the right side, they're the same. It's the distance from x to x prime on both. So like in a nutshell, what is a succinct way to describe what's going on in the yellow? The yellow justifies that the absolute value of the difference between the distance from x to the set A and the distance from x prime to the set A is less than or equal to the distance from x to x prime. And that's important for me because, the real numbers, we're using absolute value as the metric on the real numbers. So now, what do I remember? What do I recall? Well, the distance from x to the set A is f of x, and the distance from x prime to the set A is f of x prime. And so I get that the difference in the outputs is less than or equal to the distance between the two inputs. And that says that this function f is Lipschitz. Moreover, we see that it's Lipschitz with k equal to 1.